Okay, so to move on to the next lesson today, here's our problem of the day. And actually, I'm going to do this one with you because it sort of leads into the lesson we're doing today. Let x be an arbitrary number of servings of your favorite item from the cafeteria. Use the cost per item to write an equation to model the total cost of y of x items. All right, now I know lunch this year right now is actually free, right? As long as you get all the food requirements that they make you. So let's just say, I don't know, say you're in the snack line and your snack costs 50 cents, like a bag of chips or something like that. We would say our equation is y equals 0.50x. This actually is something we're going to learn today called direct variation. I think of it as, it looks like slope-intercept form, y equals mx plus b, but what's it missing? It's missing the b, or the y-intercept. So all it has is a slope and an x. And that makes sense because if you ordered 6 bags of chips, 6 times 50 cents is $3. So it gives you the total cost, and it's called a direct variation. So what is a direct variation? And we're going to model them in this lesson. Direct variation equation, y equals ax. Y is said to vary directly with x. That's how we speak it, or like to say it. Once again, there's no y-intercept or slope, so it's a simple, there's no y-intercept, so it's a simple slope times x. Instead of calling it slope, though, you see we call it constant of variation. That's the a in front of the x, the non-zero constant. Now, direct variation graph, I'm going to show you 2 of them to sort of see how to graph them. And honestly, you've gotten a lot of practice with graphing lines, so you shouldn't really have too much trouble. I have no y-intercept or b, so my first point starts off at the origin 0, 0. Now, the slope works exactly like you would graph any other line. 1/2 means I go up 1, right 2. I'll do it one more time, up 1, right 2. And I connect all the points. So what you're going to see, my line's a little crooked there, but get the idea. My line has the origin as the y-intercept. So it will always cut through the origin, 0, 0. Now how I graph this when y equals negative x, once again, still starts at 0. 0, 0, the origin. Go down 1, right 1. Down 1, right 1. And then once again, we'll connect the points. And hopefully you can draw your line a little better than I can right now. But you get the idea there. So what kind of problem am I going to give you, and how are we going to solve these? All right. So it says write and graph a direct variation equation that has -3, -9 as a solution. All right. So these look slightly different than the equation ones we've been doing in the last lesson. Let's label these. We have x and y, right? And my original formula is y equals ax. So all I do is I have xy. We're going to plug xy in to solve for a. So get -9 equals a times -3. And how do we get a by itself? We divide, right? So -9 divided by -3 equals 3. Now, I'm not finished yet. That's my slope. Do you know how, like, when you found the equation of the line in the last lesson, you found m, but you had to plug it back in? Same thing goes here. We're going to say y equals 3x. Now, this is my actual answer. So that's my direct variation equation. So you're simply dividing to get that number, right? Now how I plot it, just like we talked about the last one. I start at 0, 0. I have no y-intercept, so it cuts through at the origin. I go up 1, 2, 3, right 1. I'll do it one more time. 1, 2, 3, right 1. And we connect them. Here's your graph. So if I ask you to graph them, that's how you set them up. Now, word problems, we talked about lunch money or a snack in the lunch line. There's a lot of real-life applications to direct variation. So let's look at one with it called Hooke's Law. And if at some point you take physics, you will learn Hooke's Law. I've taught physics before, and I've taught it where a spring, how far it stretches obviously depends on the force or the weight of it. And that makes sense, right? If you have a spring, the more weight you put on it, the more it'll stretch. So it says Hooke's law states the distance d a spring stretches varies directly with the force F that is applied to it. A, suppose a spring stretches 15 inches when a force of 9 pounds is applied. Write an equation that relates D to F. So it says D to F. D is a direct variation of force. So distance, direct variation, force. So how I write that, D comes first, and even if you're looking up here, formula we got to look at, we're using different letters. We're going to use D equals, distance D, a spring stretches, varies directly with the force F. So AF. We always use A for the constant, and then it varies directly with force. So D equals AF. Now I know you could say Y equals AX, but let's stick with the letters to the problem to help us solve them. So now in A it says 15 inches, so 15 is the distance. We're solving for A, and it has a force of 9 pounds. All right, so we're going to divide both sides by 9, and what you're actually going to get A to equal, it's going to simplify to 5/3. Now remember, I'm not finished. I have to write the equation, so the only thing I plug back in is A. So I'm going to write D equals 5/3 F. And I'll put parentheses around it since it's a fraction. So that's my answer to letter A. Now, knowing that equation, in B it says predict the distance that the spring will stretch when a force of 6 pounds is applied. All right. So 6 is the force. That's why I actually like using the letters, because we know where to plug it in. Instead of saying, well, which one's X, which one's Y. So 5/3 times 6. And when you multiply them out, D equals 10 inches. So the distance the spring will stretch with a weight of 6 pounds on it is 10 inches. So here's a real life problem that shows direct variation. Now for the next part, let's see here, I'm missing one letter. Okay, so for the next part here, what happens when I give you a table? All right, we want to see if it's a direct variation. So I want to manipulate my formula for a minute. All right, what's direct variation? Y equals AX, right? All right. Well, I want to test that the constant, or the A, is the same each time. So let's solve this equation for A. It's A times X. So we're going to divide both sides by X. We're going to rearrange our equation like we've done before. So I get A equals Y over X. So what's that telling me? Is it's telling me if I take, now we don't have A, we don't have the constant, but if you look at the chart, I have a table, I have X and Y. So what I'm going to do is I'm going to actually find A, the constant, or slope, if you want to think of it that way, and see if it's the same for each of them. If it's the same for each of them, then it is a direct variation. So we're going to take a look at each one. So I'm going to call it A sub 1. And that equals, if I look at my first one, I get -1/3. All right. I'm simply writing Y over X. And think about that, the change in Y over change in X is a slope formula as well, right? Let's see what we get. So we can't simplify that anymore. It's just -1/3. A sub 2 equals -2/6, which if we simplify it, it does simplify to -1/3. All right, A1 and A2 are okay. Let's see the next one. A sub 3 -3 divided by 9, which in fact is -1/3. All right, so we're doing pretty good so far. Let's try A4. -4/12, which once again equals -1/3. All right, and we have to try the last one. A sub 5 -5/15, which in fact equals -1/3. All right, so what do you see here? You see that a 1, 2, 3, 4, 5, all 5 of them, the a or the constant is negative 1/3. So is it a direct variation? Yes. And if it's a yes, it says write an equation relating x to y. So a is the same for all the negative 1/3. So how I would write my answer is y equals negative 1/3 a. So there's my work and my explanation. So when you have a table, you could just take y divided by x each time and see if it works. All right, so let's try the next one here. Same thing. If you want to pause the video and try it first, you can. So we do y over x. So the first one I get simplifies to 7. All right, what do you notice? A2 is 9/2. 9/2 is 4.5. Does 4.5 equal 7? No, now technically you could stop there, but I'm going to write them all out. Once they do not match up, like right here, A1 and A2 are not the same, you can actually stop. We know that it's not a direct variation, all right? But if you want to continue, I'm going to continue just to write out all the work for us since it's an example. So as you can see, right off the bat, I have a lot of decimals. None of the numbers match up. So as long as the first time you see that you don't match up, you could actually stop. Your work is proving that, hey, A1 and A2 don't match, so clearly it's not direct variation. So for this one, it's no. Not a direct variation. And that's my answer. So if it doesn't work out, you just say no, and that's it. All right. So for the last example here, wanted to add one word problem and another practical application to direct variation. So it says great white sharks have triangular teeth. The table below gives the length of a side of a tooth and the body length for each of 6 great white sharks. So whether tooth length and body length show direct variation, if so, write an equation that relates the quantities. So just like before we said a equals y over x, that's the same as saying, if we go back for a second, we're going to use b equals at. All right, so I'll write it over here. B body length equals some constant a times tooth. All right, so if we know it's b equals at, we want to find a, right? So it's the same idea. We're going to divide both sides by t. So we're going to use the fact that a equals b over t. So each time we're going to take body length and divide it by tooth length. So I'm going to type them out again, and you could do them as well. Just because we're using different letters doesn't mean anything. And actually, what would this always be? This would be your x and this would be your y. And actually, I can add that. So if you didn't like using other letters, the first one's independent. It'll be your x. The second one is your dependent one, which would be y. So if that helps too, you could always do that as well. So let's see here, A1. So we get, so we get 215 divided by 1.8, which equals about, and I don't have my little approximate button here, but you put like a little squiggly equal sign. Let's keep going across here. Let's do about here. So a sub 2 equals 290 divided by 2.4, which equals about 121. Remember, it's approximate, and then A3. So we're going to do the same thing again where we're dividing each of them. So A3 will be 350 divided by 2.9. Which equals about 121. And then we have A4 equals 430 divided by 3.6, which equals about 119. A sub 3, or excuse me, A sub 5, I should say, equals 565 divided by 4.7, which is about 120. And A sub 6 which equals about 695 divided by 5.8, which equals about 120. Now this one's a little bit different because if you look, now make sure, see all these equal signs here? It should be like the little squiggly equal sign as in this. It's approximately, all right? That one doesn't look too good here. It's approximately because it's not exact. You'll get some decimals here. So we're rounding to the nearest integer. Be mindful. If you look at that, you might say, hey, you know what? There's no direct variation. I get between 119 to 121. 119, 120, 121. Normally you would say, you know what? Can't be a direct variation because of that. But here's the thing, it's real life data. Real life information doesn't always fit that. So as you see, it goes 119, 120, 121. They are all very close still. So if I did an average of it, what's my number in the middle? Or my average would be 120. If I added them all up and divided, right? Because I have two 19s, two 20s, two 21s. So my A is actually going to be 120. So this one is yes. My equation would be B equals 120T. And that's my answer. So like I said, real life situation, it's still really close enough. And even if you looked at the example before, that was not a direct variation. The numbers were all over the place. All right, so that's it for the lesson. Make sure you complete all 4 problems and get ready for tomorrow.